Hello, this is Mrs. Taylor, and I'm going to walk you through how to use the trapezoidal rule to estimate the area under a curve. So this is the basic outline for the trapezoidal rule. It's based on the area of a trapezoid, which is 1/2 base times height, and this just streamlines the process. So instead of finding or sketching out each individual trapezoid, finding its area, and then adding all those areas together, there's a pattern involved, and so this just identifies that pattern and makes the process a lot quicker. So to kind of break down what's happening here, let's say that we have a curve that looks like this, and our right bound is B and our left bound is A. So our right bound x value we can represent with a B, and our right bound we can represent with an A. And let's say we want to break this area into 4 trapezoids. So between A and B, I want to create 4 trapezoids, and I want them all to be the same width. So first trapezoid, second trapezoid, third trapezoid, and fourth. And let's represent this as, if this is A, let's just call this A sub 1, A sub 2, and A sub 3. And so for each of these x values, I will create a trapezoid, or a base of a trapezoid. And the way I do that is I create vertical lines that attach to the curve at each x value. So at our A value, our A sub 1, A sub 2, having mouse issues here, A sub 1, A sub 2, A sub 3, and then our right bound, which would be B. And the idea is that we would connect these y values with a straight line to create trapezoids. And this is considered to be more accurate than the rectangular approximation method, because the trapezoid resembles more the behavior of the curve than a rectangle. And so if you think about it, the definition of a trapezoid is a quadrilateral with one pair of parallel sides, and the 2 parallel sides are called the bases. And so these vertical lines on our graph are the bases of each trapezoid. And so if I were to find the area of our first trapezoid, I would do 1/2 times the base, which is, 1/2 times the height, which is the distance between these two x values, times the bases added together, which will be the length of these 2 vertical lines. And so that would be, for this curve, this y value and this y value. And so for our first trapezoid, we'd use this base and this base. Our second trapezoid uses this base again, and then this base. Third trapezoid, this base again, and then this base. Fourth trapezoid, use this base again, and this base. So that's where the 2's in this rule come into play. These y values represent the length of each base, and each base in the middle, not the left bound or the right bound, would be used twice in the area formulas. So that's why the trapezoidal rule has the 2's instead of just adding up all the y values. And the b minus a over n represents the number of trapezoids, b minus a represents the distance from your left bound to your right bound, and so it's dividing up this interval into equal subintervals, and so it gives you the height of each trapezoid. So let's do a sample problem. And in this problem it says use the trapezoidal rule with n equals 4, that means 4 trapezoids, to estimate the definite integral, and compare the result with the exact value of the integral. And so for purposes of this video, we'll just talk about the first part, how to estimate the definite integral using the trapezoidal rule. And remember, a definite integral is basically a sum. It's a limit of a sum. And so what they're saying here is your curve is x squared. You're on the interval from 1 to 2, so that would be your a and your b values. So this is your b, this is your a. F of x is x squared, and you have 4 trapezoids. And so using this setup, we have 1/2 times b minus a over n. So 1/2 times b minus a, which would in this case be 2 minus 1 over n, the number of trapezoids, which is 4. And then what I would do is I would find my y sub 0, y sub 1, y sub 2, and so on, which are the y values when I plug in the x values for the bases. And so I'm going to make a t-chart really quickly and do that. So there's my t-chart, and I need to think about what my x values are going to be. My first one, my left bound, will be 1. But I've got to break up the interval between 1 and 2 into 4 trapezoids. So I need to go from 1 to 1.5, that'd be the first, 1.5 to 2, that's only 2 trapezoids. So I have to break it up even further into fourths. And if I wasn't sure what the distance would be, all I'd have to do was evaluate 2 minus 1 over 4 to find out that each trapezoid would have a width of 1/4. And so here are my x values, and it's probably better to write f of x instead of y. So what I would do is I'd take each of these x values, plug it into my function, which is x squared, to get the f of x value, which is the length of the base of each trapezoid. So here are my corresponding y values, and all I have to do now is complete my sum. And so I would take the first y value, add it to 2 times each middle y value, and then add 4 at the end. My sum would look like this, and I know that the original rule has a 2 times each y value, but all I did was write it in factored form, so 2 times each middle y value. So all you would do is evaluate this in your calculator, and you would have the estimate, which would be 2.34375. And so my estimate of what this integral would be, using the trapezoidal rule, is 2.34375, which means that the area under the curve, if I graphed x squared between 1 and 2, is approximately 2.34375. Eventually in class we'll learn how to evaluate this integral algebraically, but if I wanted to check it in my calculator, I could do that. The calculator will evaluate a definite integral for me. And so what I would do is I would go to math, and it would be option number 9. This is definite integral. And I would enter my bound, so 1 is the lower bound, 2 is the upper bound. Enter your function, and then you integrate with respect to x, press enter, and it gives you the estimate. And so the calculator is estimating 2.33. Our estimate is 2.343 or 344, which is pretty close. And so we we did it correctly. And that is how you would use the trapezoidal rule to estimate the area under a curve.